on finite element analysis. In this session, we are going to discuss about consistent and lumped mass matrix. In the context of structural dynamics and finite element analysis, mass matrices play a crucial role in representing the inertial properties of a structure. Two common types of mass matrices are the consistent mass matrix and the lumped mass matrix. Consistent mass matrix, as you can hear the word in it, consistent, it simply means that suppose if you're talking about a particular beam analysis wherein you want to assume it's fun and fixed, which means it is going for actual vibration problem. So you can go through the model analysis that I have shown you to understand this. If you consider that the mass is uniformly distributed over the body, you would say that you are going for consistent mass matrix analysis. But suppose if you assume that the entire mass of the beam is divided into half and each half is arrayed at the two ends of the beam, then we will call it as lumped mass matrix. Now we'll first discuss about consistent mass matrix. The consistent mass matrix is derived by considering the exact shape function used for displacements in the element formulation. It is based on the integration of the element mass over its volume and takes into account the varying distribution of mass within the element. So you can basically talk about the mass being consistently distributed over the body. That is a way of saying, or you can assume that it is mass over volume distribution over the body. So you can just take an overall integration and solve and calculate for its mass matrix. The integration process involves the use of numerical integration techniques such as Gauss quadrature to evaluate the mass contributions at various points within the element. So say the element is divided into n number of nodes. So what will be the mass contribution at each node is what you can calculate. Accuracy. The consistent mass matrix is considered more accurate but can be computationally expensive, especially for higher order elements. I'll show you why. This is an example of a mass matrix that you can see. You can see that these numbers are evenly distributed over the entire matrix. So what happens is if the order of the equation increases, then this matrix will keep on increasing and so will these values keep on distributing randomly over the body. So the computation speed required will be more and hence you need to have better computing solutions for it. So that's why it becomes a little bit more expensive, but it is going to be more accurate as compared to lumped mass matrix. Now we'll talk about lumped mass matrix. The lumped mass matrix, on the other hand, assumes that the mass is concentrated at the nodes of the finite element. As I told you, this implies that the mass distribution within the element is approximated as a set of point masses located at the element nodes. Now here suppose if you consider the entire beam to be distributed into two elements, then we can say that there will be three nodes. So your mass will now be distributed amongst the three nodes. And in consistent mass matrix, if you have three nodes, so it will be consistently divided over the entire beam. And when you talk about the software, you don't have three nodes, you have n number of nodes. So at each node, the mass is distributed equally. The lumped mass matrix is obtained by summing the masses at each node. Each diagonal entry of the matrix represents the total mass associated with a specific node, and off diagonal entries are typically 0. So I'll just show you an example. You can see here, this is a diagonal that you can see 1 L square by 12. So this entire 3 by 3 is one element. Here also this is one element, all 0. This is one element, all zeros, and here again you can see the fourth element. So you can see here this diagonally whatever is applied is the position where you have placed your mass. So that's the meaning of this lumped mass matrix, and the rest of the elements will be considered 0. Simplification. While the lumped mass matrix is computationally more efficient, it is a simplification and may not capture the true distribution of mass within an element as accurately as the consistent mass matrix. So you will fail here in accuracy as compared to consistent mass matrix, but definitely you will be computationally more efficient because you can see that the masses are added only at the diagonal and these are all zero. So you basically save a lot of space when you are computing it, and so you get better solutions at low computational configurations. We'll talk about the comparison between the two. The choice between a consistent and lumped mass matrix depends on the specific requirements of the analysis and the desired balance between accuracy and computational efficiency. So you need to decide which is more important for you for your solution, and accordingly you can choose between the two matrices. In dynamic analysis, where mass distribution is critical, a consistent mass matrix is often preferred for accurate results. In certain cases, especially for linear elastic structures and where computational efficiency is a priority, a lumped mass matrix may be sufficient. So these are the two cases which discusses about the specific use of consistent and lumped mass matrix respectively. So we'll just have a overall discussion on this topic now. Both types of mass matrices are used in the context of finite element analysis to model the dynamic behavior of structures subjected to various loads and boundary conditions. You can go through the videos where I have explained you the modal analysis of an axial beam and a transverse beam, wherein we are discussing about the modal analysis of the beams. And also I have given you the finite element solution of that problem. So this is just a theoretical discussion about the problem. So once you go through the problem and the analysis, you would get a better understanding of it. The selection of the appropriate mass matrix depends on the specific characteristics of the problem being analyzed and the available computational resources. So that's all about the consistent and lumped mass matrix which is used in finite element analysis. With this, I end the session. I hope you have understood the concept. If you have any doubts, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.